Alright, lesson 119, one of the main focuses here for the next couple of chapters is now parallel circuits. So we've covered series circuits in pretty good detail. We're now going to move on to parallel circuits. If you know anything about this already, when we wire something in the field, we're always going to use parallel circuits with very few exceptions. And as we go through this, I think it'll kind of become obvious why. But here again, just a quick reminder, we know a series circuit, there's only one path for current to flow. If you remove one of those loads or one of those resistive elements, we have an open circuit. The circuit no longer works. Parallel is the opposite of that, right? We have more than one path of current flow, as you can see here. And what happens if we remove any number of these elements? Well, let's remove one. You see that the other two still function. We still have current flow. We don't have through the first one, but the other ones are unaffected. And we can even remove two of the three. And effectively, if you forget about those first two, this is just simply a circuit with one element or one load to it. So another good thing to keep in mind is sort of every one of those elements or loads has a direct path right back to the source, right? So we have sort of these sides of the ladder, if you want to look at it as a ladder. They connect all loads back to the source directly, okay? So keep that in mind too as we learn our different calculation rules as we go here. So just with series circuits, we have some 4 specific rules that apply to parallel circuits. Some are the same, some are a little different here, so you want to make sure you're on your toes. Make a note of this. You're going to be using these rules time and time again throughout your worksheets, right? So first one, let's start with the voltage rule, right? So total voltage in a parallel circuit is equal to the voltage of element 1 and element 2 and element 3. Again, that goes back to sort of how we have this direct connection from any element back to the source here. So that's another reason why we wire everything in parallel in the field, right? If I wire up a bunch of lights, I connect them in series, they're all going to have some fraction of my source voltage. If we wire in parallel, every single load gets the intended voltage, usually, let's say 120. Every one of my lights, if these loads are lights, everyone gets 120 volts, regardless of the other ones. Okay, next rule, amperage. Okay, in this case, amperage is additive, all right, in a parallel circuit. So I total equals I1 plus I2 plus I3. So another way to look at that is, our current flows out here. Let's say each one of these draws 1 amp for argument's sake. Current flows out through this leg. We have 1 amp that goes here, up through this load, and 1 amp goes back. We have another amp that goes out this way, up through this load, and back. So you have to consider on this portion of the circuit and on this portion of the circuit, we will have the added of both of these loads, and we'll take that one step further. We have 1 more amp that flows this way. So actually on this circuit, or this portion of the circuit, we have 3 amps. On this portion, we have 3 amps. We only have 1 that goes up through here, so we kind of lose 1. So on this portion, now we have 2 amps, because we're still carrying the loads from these two. Same with this portion of the circuit, we have 2 amps. We kind of drop 1 as it goes through here. So we now only have 1 amp flowing through this section again here, till we join back up with this load and sort of gain that amperage back. So you can see at any different point of a parallel circuit, the amperage is going to be different depending on how many loads are being powered on that portion of the circuit. And the book has a nice diagram on this as well. So next is your resistance rule. You can see this is kind of a big ugly formula here, and quite honestly I'm going to show you some ways to avoid this formula at all costs, because from a algebra point of view this thing's kind of a mess. Just quickly, if you do find yourself stuck using this formula, pay attention to order of operations. You're going to have to do your parentheses first, this parenthesis, that parenthesis. Then you can go ahead and really you're going to have to add up this denominator. Then you can do 1 divided by the denominator. That's ugly. Again, I'm quite sure we can avoid this formula through a couple little tricks and creative thinking, and I'll show you some of those ways. And then next here you're going to have your wattage, your power. That's just additive. That's not going to change from series or parallel. So we'll kind of throw these rules up over here. Remember those. The other piece we need, of course, is Ohm's law. Just like with series calculations, we're going to need to reference this as well. So let's just kind of make up a problem here with 3 loads. We have R1 in this case, and just think of them as incandescent light bulbs if it helps. We have 60 watts at 130 volts. We have 75 watts at 120 volts. And 100 watts at 110 volts. Okay. So hopefully this isn't a surprise. I'm going to put up another one of our little table charts here. So again, as with series, they've got to tell us the source voltage or the total voltage, right? That's kind of your free space if you want to think of it that way. But what's really nice about parallel circuits is this formula up here, the voltage formula. E total equals E1 equals E2 equals E3. So essentially by telling us the source voltage or total voltage, we now kind of get that whole top row, that whole voltage row filled in. So that's an inherent upside to parallel circuit calculations for sure. So if you're looking at this, what's the next thing we can do? And quite honestly, there is only one move to make. Hopefully you know what I'm about to say. We've got to find fixed resistance, right? We never get away from that. So I'm not going to spend a lot of time talking about the Ohm's law. You guys know that by now. But naturally, we're going to use the formula R equals E squared divided by P to find resistance. If we go ahead and work that out, we're going to find R1 is 281, R2 is 192, R3 is 121. Again, we just use Ohm's law to find that based on our rated values, right? Use rated values, find fixed resistance, enter them in the table, right? So now we have some options here, right? Because we have 2 values in all 3 of these columns, we can now again use Ohm's law to find whatever we want to find, I or P in this case. I'm going to go ahead and choose, let's work with I. So we know E, we know R, we're looking for I. Ohm's law tells us I equals E divided by R. Once again, I won't run you through the calculation, you guys can do that, but you know, in this case, I1 would equal 0.426, R2 would equal 0.625, and amps of R3 would equal 0.992. Okay, so one thing I didn't really point out is, and I'm just going to back up a couple steps. We could have found R total down here using that our resistance formula. I really don't want to do that, and we don't have to. So again, back to where we were. We found I. The way we work around not using this resistance formula, let's actually use the amperage formula. Now we can use that because we have the other 3 values. Right, so I total equals I1 plus I2 plus I3. Go ahead and work that out. You get 2.403 amps. Now what we've done, we can find this R total value by simply using Ohm's law, right? So again, we're looking for R. We have, in this case, E and I. Do that math, you get 49.938. So now we've got everything except for power. And really, the only next step we can take is an Ohm's law step. We don't have enough information to use this formula at this point. And I could find any of them I want. I'm going to go ahead and start with R1 over here. So again, if we are looking for power, looking for wattage, we're going to use P equals E times I from Ohm's law. So if we go ahead and work that out, we have 51.12 watts for R1. Same thing for R2, we get 75 watts. R3, we get 119.04 watts. So at this point, it's kind of a good point to stop and check ourselves, right? So we're giving R1 120 volts, and it's putting out 51 watts. So if you think we're feeding it with a little bit lower of a voltage, putting out a little bit lower of a wattage. So we know that sounds like a pretty good logical answer. Now this next one is interesting. We got 75 watts. Well, what do you know? It's rated 120 volt. We gave it 120 volt. It's rated to put out 75 watts at 120 volt. So stands to reason it will put out 175 watts in this case. So anytime you're actually operating something at its rated voltage, it may not be necessary to find fixed resistance because it's going to put out its rated wattage or its rated amperage. The book doesn't throw a lot of those at you because that'd be a little too easy, but don't overlook that. It could be a nice shortcut. And then power for R3, wattage for R3 is going to be 119.04. Once again, the thing's rated 110 volts. We're actually giving it 120. So we're getting out just about 20 more volts than or 20 more watts than it's rated. Again, the wattage went up just a little. Makes good logical sense there. So now we could use Ohm's law, but we also have this other set of rules we shouldn't neglect. P total equals P1 plus P2 plus P3. So we can simply go ahead and do that. Of course, that gives us 245.16.